So in metallic bonding, metals bond with other metals and sometimes nonmetals to form metallic bonds. So metallic bonds are formed when the atoms give up their valence electrons to become positive, and the electrons are then free to move through the substance. We call this the sea of electrons and is responsible for many of the properties of the metals. So in the top picture on the right, the little GIF, we can see we've got our metal atoms. They've given up their electrons, and those are the little red dots flying around. The electrons are free to move between different atoms. They're not stationary or stuck to just one. This allows for the first property, which is malleability or ductility. So metals are malleable, meaning they can be squished or molded into different shapes. They're also ductile, so we can feed them into smaller and smaller smaller and smaller diameter tubes and stretch them into metal or into wires. So their ability to stretch and squish like that is based on the sea of electrons. So since the atoms are partially positive, as we can see in the picture, we got that little lowercase delta symbol, and with the positive charge, that shows that they're partially positive, and then they have the electrons moving all around. So they're not bonded in a particular place. So the atoms are able to slide past one another and change the kind of overall shape of the metal structure. We also have that the metals are conductive. So at the picture at the bottom, we have the partially positive metal atoms with the electrons moving through it. So if we had a negative charge on the left and a positive charge on the right side, so like hooked up to a battery, you know, our batteries have a positive and a negative end. If we hooked up the negative to the left and the positive to the right, the electrons would be repelled from the left side and attracted on the right side and would move through the substance. And that's essentially what electricity is. It pulls electrons through a substance. We call these bonds in metals non-directional bonds because they aren't like a line connecting atoms like we see in covalent. The bonds or attractions are everywhere, and the electrons are shared equally by all of the atoms. So they're non-directional. Now, metallic substances have different types to them, and they are called alloys. These are mixtures of metals. Now, we don't see chemical formulas written for alloys. We typically just list the elements that are in it. We might say that they're put a little plus sign between them, or just say that they are an alloy. So metals mix with other metals and sometimes again non-metals to form alloys. These mixtures of metals are often stronger and harder than the pure metal alone. There's two types of alloys that we have. The first one is substitutional, and we can see that in the picture above, where the atoms are of similar size and are mixed and substitute for one another. So brass is a good example of this. Zinc and copper. Zinc and copper are right next to each other on the periodic table, so they have very similar atomic radii. They're similar in size. So if we melted zinc and copper together and mixed it, we would get a zinc-copper alloy or brass, and the atoms would just the zinc and copper would replace each other, kind of substitute in for each other because they are of similar size. So that's how we actually make these. We're not going through a larger chemical reaction to make these bonds. We're just melting and mixing the substances. And certain things, they can do certain things when they cool the substance or when they mix them to cause certain structures to form, but essentially they're a mixture. Then we have interstitial alloys, which are where atoms of smaller size fit into the interstitial or in-between spaces of the pure metal. So that's the one on the right up above. We have the little darker green atoms that are fitting in between the spaces of the red atoms. So they're not substituting for the red ones, they're fitting in between. So a great example of this is steel. So steel is iron that iron atoms that are a little bit bigger, and then we actually add carbon to it. So carbon is the smaller atoms that fit in between in those interstitial spaces, and it strengthens the metal because it doesn't allow for that malleability as much. Okay, it strengthens the bonds between them by filling in those spaces. So we get a stronger substance. And there's multiple kinds of steel. So you have low density carbon steel, we have high density carbon steel, and those can have different strengths to the substance. So these chemicals, these alloys are typically harder, less malleable because the atoms in between interfere more with the movement of the alloy when it's trying to be molded or hammered, and it makes it harder for the atoms to slide past one another. So we get these stronger substances. Metallic substances have some other properties that we should be aware of. Typically, their melting points are high, with a few exceptions. When melted, the atoms start to separate and break those metallic bonds, and we get these individual atoms. They're all separating from each other. So we have typically high melting points. There's a couple that are low. Mercury is one. It's one of our liquids. It's on the periodic table. Another good exception to that would be gallium, the element gallium. Its melting point is pretty low. It's not a liquid at room temperature, but our body heat can actually melt gallium. So gallium would melt in your hand. Boiling points of these substances are also typically high. Usually if melting point is high, then boiling point is going to be even higher than that, of course. And that the atoms will separate completely, breaking all metallic bonds, turning them into a gas. They have high luster, so our metals are typically really shiny. Sometimes when you see a dull metal, it's because it gets a coating on the outside. A lot of them will react with the oxygen in the air, and we get an oxide layer on it, meaning like if it's iron, it gets iron oxide on it, and that's just rust. Or if you have silver and like jewelry, sometimes we'll get a dull kind of color to it or a darker color to it, and that's because it has that oxide, like silver oxide layer. So you can shine it up and you get that luster again. Metals conduct heat and electricity very efficiently, very well, so they're good conductors. All right, let's take a look at how questions might be asked about metallic bonding and metallic structures and alloys. So typically you'll be asked things like the type of alloy certain elements might make together, how the structure of the alloy or metal would look. So they might give you pictures and you're picking the right picture of the structure. And I've also seen questions where students have had to draw an alloy. So let's take a look at an example and how we can make some decisions on this kind of question. So first, this question says rose gold is 75% gold and 25% copper. Draw an alloy of copper and gold with showing if it is an interstitial or substitutional alloy with 16 atoms total. Use open circles for gold and shaded circles for copper. So there's a lot of key elements in this. They want us to show the alloy. They want us to show what kind of alloy it is, interstitial or substitutional, so we have to make that decision. It wants specifically 16 atoms, and it's telling us how to draw those atoms, open and shaded circles. So we know we want 75% to be gold and we want 25% to be copper. So I'm going to just start with how many atoms each that is. So 75% or 3/4 of 16 is going to give us 12 atoms, and then the other quarter of the 16 is going to give us another 4 atoms. Okay, so this, we want 12 atoms of gold and 4 atoms of copper. So that's our first little decision there. Over here, they also give us the radius of copper and gold. Now, we want to determine what kind of alloy it is. Well, for it to be substitutional, they need to be no more than 15% different in their size in their radius. So the way we can figure this out is we can just divide these two numbers and multiply by 100 and then see what percentage copper is of gold in terms of the radius. So 127 out of 144 gives us about 88%. So they agree about 88%, or they're similar about 88% of the size, and that's within 15%. So we can go all the way down to 85%, and they can still be substitutional. Below that, we'd start to get into our interstitial alloys, where the smaller atom would fit inside the spaces of a larger atom. Okay, so now what I'm going to do is draw in my 16 atoms. I've been given a box here. I want to fill up my box. I want to show that it's a solid, so I'm going to go ahead and fill in my atoms. So 3, 6, 9, 12. Oh, this is only going to fit 15. Let me edit this just a little bit. We need 16, so let's do 4 by 4. It's not perfect, but we want to show that nice arrangement of our atoms and fill up our space. So we're showing that it's substitutional by the atoms being similar in size. Now we want to do our shading of our 16 atoms to show that 12 of them are gold. Now, with alloys, there's no real pattern to it. We just want some of them to be gold and some of them to be copper and spread it out. Our shaded ones need to be copper. So we only need four of them to be shaded in. Pick 4 random ones. Here's one. Here's one. They might be next to each other. And there's 4. So we have answered all the parts of the question. We've drawn 16 atoms. We've shaded in the copper, which is only 25% of the atoms. We have left open circles for the other 75%, which are the gold atoms. And we've shown that they're substitutional by having them about the same size. I'd probably clean it up a little bit if I was doing this on my test, but this is an answer that we can use. So again, we want 15%, no more than 15% difference in the atoms. An easy way of, in their radius, an easy way of doing that is dividing the radii if those are given. If you're not given a radii, I'd say that within the same row, within 2 rows of each other on the periodic table, they're going to be pretty similar in size. We can see where gold and copper are on this periodic table. So within 1, 2 rows, especially if they're in the same section. Now, if I had something like iron here, and we know carbon, which is 2 rows up, but much more further to the right, our nonmetal there, that's going to be much smaller, and we're going to get more than a 15% difference. So those end up being interstitial. So those are some ways to judge it if you don't have actual numbers given. So those are some examples. You'll get some more examples, especially on some multiple choice questions on your practice for this section. Definitely ask questions and get some help if you need it. Thanks.